Reactions of alkenes and alkynes. This is the point in the class where, So you may have thought this class was a lot and overwhelming so far. I agree. But sadly, it's probably about to get a little worse before it gets better. Wait, what? Yeah. So we spent a little while talking about reactions of alkenes and alkynes that go through carbocations. 3 videos, in fact. 3 videos of alkenes and alkynes that go through carbocations. We're about to blow through a lot of other reactions that don't go through carbocations. So we spent a lot of time on the carbocation thing because carbocations are important in the long-range scope of organic. The reactions we're about to roll through really only apply to alkenes or alkynes. So my advice to you is pay attention, watch these videos a lot of times, work a lot of problems, and stay on top of it. Because if you don't stay on top of it, things can snowball very quickly this week. I have faith in you. You can do this. Let's do this. So the first reaction we will talk about that does not go through a carbocation is addition of halogens. The addition of halogens reaction makes this as a product. All right. That's not good enough. That's not all you need to know. You need to know how that product forms. So let's talk about how that product forms. The mechanism for this reaction is as follows. Alkene, that's the nucleophile, attacks the Br. The Br is a really big guy. He's got a large atomic radius. He says, I don't have to take that. I'm going to attack back. The bromine in this reaction acts as the electrophile and the nucleophile. He gets attacked and he attacks back. Weird. This bromine says, do your own thing. I'm gonna go this direction. I'm gonna leave you alone. So what you get out of those 3 arrows up there that happened all together is this as a product. A 3-membered ring with a bromine in it. The 2 carbons from your alkene are the 3-membered ring along with the bromine. Okay. The bromine up there, he had 3 lone pairs. Now he's only got 2 lone pairs. Bromine's in group 7. In that molecule, he's got 6 electrons. Bromine is a +1. Yep. This intermediate is known as a bromonium ion. What is a bromonium ion? It's got a bromine. means a bromine with a positive charge. Addition of halogens always goes through a halonium intermediate. Did you hear me? It does not go through a carbocation. It always goes through a halonium intermediate. Halonium can mean chloronium or bromonium, and a weird occurrence of iodinium. Fluorine doesn't do this reaction. You need to have a large atomic radius so that you can hold on to both carbons at once, and bromine, chlorine, iodine are the ones that are big enough for that. We'll talk a little bit more about iodine, but really not much. We'll see bromine and chlorine do this all the time. So after my bromonium, how do I get to the final product that's given up there? Whoops, it's supposed to be blue. My final product, bromine, the bromide actually, that departed earlier, that bromine says, I'll help you out, bro. Let me bust open that ring for you. The bromine, the bromide, attacks one of the carbons of your bromonium ion, and that three-membered ring gets busted open. That carbon's already making 4 bonds, and so if this one tries to make a new bond, you have to break one of the old bonds as well. Carbon cannot make more than 4 bonds. Don't do that. So we attack the carbon, bust open the bromine, bust open the bromonium, and we get our product. Well, our product as the constitutional isomer that we're supposed to make, but we haven't yet discussed stereochemistry. In order to talk about the stereochemistry of the reaction that happens, you have to understand the mechanism. So this top step has 3 curved arrows happening all together, all in one step. This first addition is called concerted. What does it mean to be concerted? In concert, all together, all 3 arrows happening all at once. We're doing a concerted step on this alkene. Alkenes are sp2 hybridized and trigonal planar. So this alkene being planar means some consequences has some consequences on our stereochemistry. So when bromine gets attacked and attacks back, because it's happening on a planar molecule, it means that bromine has to be attaching to one face or the other. We could say that that bromine gets attached to the top face, like this, and put two wedges on that compound. Bromine could also get attached to the back face. Hold that thought, we'll come back, I think. So, because I have a trigonal planar thing, when the bromine sits down across that pi bond, he's going to attack and sit down on the top face or sit down on the bottom face. And we get this when he sits down on one face or the other. This is sitting down on the top face. Alrighty. So then when bromide attacks that carbon, this bromine is sitting on the top face, covering up, occupying all the real estate on the top face. So this other bromine has to do a backside attack. It has to attack from the rear so that, because this bromine is taking up all of the space on the other side of the ring. So what that leads to is inversion at the stereocenter where you attacked. So I get a dashed BR. It leads to retention at the stereocenter where my bromine was hanging on all along. What? That was fancy words. This carbon did not participate in this step whatsoever. So that carbon should retain its stereochemistry, aka it should stay the same. Bromine was wedged, bromine is wedged. This carbon got attacked from the back side because the top side was occupied. It got attacked from the back side, the bottom side, and inverted that stereocenter to get me here. So I end up with this product with this very specific stereochemistry. This product is called the anti-addition product. You ever heard of anti? This anti-addition product says the two groups that got added to different faces of my original alkene. One got added on the top face, one got added on the bottom face. Anti-addition. Remember, the reason bromine does anti-addition is because it goes through this bromonium ion. This bromonium ion is formed in a single concerted step, and that single concerted step means you get the bromine on the same side here. So the very first reaction, I hope I explained this well. This very first product is a syn product because the two bromines are on, the two bonds, bromine to carbon, are on the same face. But when you bust open that ring, you end up with anti-addition overall. So we do not say that this does syn addition. We say addition of halogens always does anti-addition. What we're saying what we're meaning when we say that is the final product is always anti-addition. Yes, it went through a syn step, and it's because of this syn step that we resulted in anti-overall. So don't ever tell me that bromine does syn addition overall. It's not true. What I'm saying is we will never, ever, ever get this product out of this reaction. Never, ever, ever. Not happening. Okay, so because the mechanism works like this, we end up with an anti-addition product. Is this blue anti-addition product the same as this black anti-addition product? Nope. What's the relationship between the blue and the black? The blue and the black things are enantiomers. So apparently this reaction creates a pair of enantiomers. How the heck did that happen? At this point back here, bromide attacked that carbon, but there was no difference in substitution here. These are both secondary carbons. At this point, the bromide attacked this carbon, but there's no difference in the substitution here, so either carbon could have been attacked. So if I, instead, that bromide, attacked the bottom carbon, because there is no difference in the substitution of the top carbon and the bottom carbon here, attack the bottom carbon and bust open that bromonium ion, I get this tiny purple product. Where the bromide attacked here, inversion should happen at that stereocenter. Done. This carbon, the purple version, this carbon did not get attacked. It stays the same. Done. So the purple and the black are the same. The blue and purple, blue and black are enantiomers. This reaction creates a pair of enantiomers. Just as a word of caution, without going too far down that rabbit hole, don't think that addition of halogens always creates a pair of enantiomers. It frequently does, but I'm adding two of the same group to my two alkene carbons. That could lead to symmetric products and could lead to meso compounds. Oh, not here, not here, not here, but it could. This product is tied into a cyclo compound. Cyclos cannot rotate, so this will never be meso. But sometimes in acyclic compounds, you might get meso products. That's almost enough about bromine. The final little thing I want to say about bromine is bromine makes an important qual test for alkenes. What is a qual test? A qual test is something that shows you a quick yes or no answer. A qualitative testing, which we will always talk about, a qualitative testing to spot a certain functional group. Bromine, liquid bromine, is a red compound. When you run this reaction, it starts out as a red liquid mixed with a different thing. Over the course of the reaction becomes less red because the Br2 is disappearing. So this qual test stuff says if you have a solution of something that is unknown and you add bromine to it, if that red color disappears, it's confirmation that your unknown had an alkene in it. If you have a solution that is an unknown and you add red bromine to it and that red solution stays red, it tells you your unknown solution did not have an alkene in it. Qual tests tell you quickly, on or off, did I have this functional group or not? If the red goes away, you had an alkene or an alkyne. If the red stays, you did not have an alkene or an alkyne. Whew, yeah, okay, done. So that last one was addition of halogens in non-nucleophilic solvents. So I did not point that out in the last one, but our solvent back there was CCl4. You might have seen CCl4 on the bottom of the arrow. I didn't touch it. It wasn't part of the mechanism. It didn't have any bearing on what the product was. It was only there to make sure everything was soluble together so that they could react. Well, nucleophilic solvents do participate in the reaction. Water is a nucleophilic solvent. A lot of solvents that have hydrogen bonding are nucleophilic solvents. CCl4, no hydrogen bonding, non-nucleophilic. Does not participate, you had two BRs. Okay, let's see how the mechanism would work if we had a nucleophilic solvent like this one. BR, alkene attacks, bromine attacks back. Let's just go on, do your own thing. Bromine hooks up like this, and we make a bromonium. We do have bromide in solution, but we've also got water in solution. When we've got bromide and water, we have to consider who's present in larger quantities. The thing on the bottom of the arrow, especially in the beginning, is often listed as the solvent. So the solvent is present in large numbers of moles, while you only add a little bit of Br2 to the solution. The little bit of Br2 serves to react like this and make that bromonium. But once you have a bromonium, there are thousands more water molecules than there are bromide molecules. So it's statistically much more likely that the water is going to attack and bust open that bromonium like so. Water attacks, bust open the bromonium, so I get water attached on one side, water that brought along both hydrogen buddies, and the bromine is still up there. That's not good enough. Water needs to come clean up the mess he made. Clean up, everybody clean up. Ooh, we squeezed it in the corner over here. We get that product. That constitutional isomer. Here's the way I drew it as a stereoisomer. Why did I do that? That to me looks like anti-addition. Yeah, because I went through a bromonium. That bromonium would be like this. Wedged or dashed. And when that water busted it open, it's going to bust it open on the opposite side from where the bromonium was. So I get this stereochemistry. Ooh, that squeezy over there. This product is that product. Is that the only product that's made? Nope. I would also make the enantiomer of this. How does that work? The exact same as the last example we just discussed. Water could attack this top side up here instead of the bottom. Water could attack this top carbon, bust it open. OH would be dashed up here. Bromine wedged down there. Did you hear me? Bromine would be wedged down there, and water dashed up here. Is that blue molecule and that blue molecule the same? Yes. All I did was pick this one up and flip it over, like flipping a pancake. Pick this one up, flip it over. I got an OH pointed down up there. It becomes an OH pointed out down here. BR pointed back. That comes from a BR pointed up. Yep, flipping a pancake. That's all that I did to get from here to there. So once again, this reaction creates a pair of enantiomers. Would you expect the product as obtained in this reaction to be optically active? No, because you have a racemic pair of enantiomers. A 50-50 mixture of the blue one and the black one, 50-50 mixture, racemic mixture. All right, I think I get it. Bromonium is important. Let's do another example. Uh-oh. What's different about these examples? There is a difference in the top carbon and the bottom carbon. That top carbon is a tertiary carbon. The bottom carbon is secondary. How does that change the mechanism? How does that change what happens? I'm going to actually draw the mechanism of this bottom one, and you should attempt the mechanism of the top one on your own, but let's draw the bottom one together. Br. Alkene attacks the bromine, and the bromine attacks back. But the bromine should always attack the more substituted carbon, because that carbon has better carbocation character. What? Better carbocation character. What is that? This bromonium is not a carbocation, but it has some characteristics of a carbocation. This carbon is partially positive because the bromine's yanking on it. This carbon is also partially positive because the bromine's yanking on it. Which one can handle that partial positive better? Which partial positive is more stable? The one that's more substituted. So this carbon that is tertiary has better carbocation character than this carbon that is secondary. I'm going to repeat, even though you could rewind. This carbon that's tertiary has better carbocation character than this carbon that's secondary. What that leads to is when my nucleophile is methanol this time, when my nucleophile attacks that carbon, when my nucleophile attacks the bromonium, it always attacks the more substituted carbon because that carbon has better carbocation character. Ugh, a mouthful. So I end up with CH3 because that methanol brought his CH3 and his hydrogen along for the ride, and the Br connected down there. I should have also said methanol is a nucleophilic solvent. How do you know it's a nucleophilic solvent? Because it has hydrogen bonding. So methanol, another methanol molecule, there's lots of methanols around. Another methanol molecule cleans up the hydrogen mess that's left, and we get this as our product. Ta-da! Isn't it lovely? Yeah. That's not the end of the story, unfortunately, because we also have to consider stereochemistry. That bromonium is going to be a concerted thing. It's going to make a syn-bromonium. Bust open that syn-bromonium, you get anti-addition overall. That's going to lead to my Br and OCH3 being anti. Br and OCH3 are anti. But what happens to this methyl? This methyl goes along for the ride. So back here, if my bromine is wedged, that's going to force my methyl to be dashed. Okay. Then I go through and invert that stereocenter, this one. That's going to lead to bromine still dangling off wedged down here. The methanol had to attack from the back. And methanol having to attack from the back pushes the methyl out of its way. So that pushes the methyl forward. So when the methanol attacks from the back, the methyl has to get pushed forward. If methanol had attacked from the top side, that pushes the methyl backwards. So we get the purple isomer, but we get the two blue enantiomers as our real legit final products, including stereochemistry. So this is the right isomer, but these products are my legit final products because of stereochemistry. If you're awake and paying close attention and really following along, you say, hold up, how did you make this isomer? Because what you have drawn below, I can definitely see how that turns into this bottom blue isomer. But how did we make that orange circled isomer? Okay, I can explain. When I make the bromonium, I said the bromine has to sit down on one face or the other. So I've drawn it as the bromine sat down on the top face of this alkene. And my bromine's coming forward. Just as easily, that bromine could have sat down on the bottom face of my alkene, leading to the bromine going backwards and the methyl coming forward. Then when methanol busts that thing open, methanol always has to attack from the back side. Oh, I forgot my plus on my bromine. Methanol always has to attack from the back side, and that's where I lead to bromine going backwards down there, methanol coming forward up here, and that methyl has to bend to the wishes of the methanol that was the attacker. Yeah? Clean up this orange thing down in the corner, and you get that top blue that has an orange circle. Whew, yeah, that was a lot. The reason I didn't have to talk about two different bromoniums forming for the last two examples was if I drew the bromonium in the last two examples, if I drew the bromonium going forward, it was an identical molecule to the bromonium going backwards. In the last two examples, the bromoniums were meso compounds, so I didn't have to consider two different bromoniums. But this one and this one, these are definitely two different bromoniums, not meso, so that's how I really led to both enantiomers being created. Okay. So when you're drawing this top reaction on your own, you're definitely going to draw this top reaction on your own, right? When you're drawing this top reaction on your own, you do not have to show me the purple path and the orange path. When you're just drawing a mechanism, you can draw a mechanism that does not include stereochemistry in the mechanism. However, at the end of the mechanism, you should add stereochemistry to the product or products that you make. Stereochemistry does not have to be part of the mechanism. It should be in the end products. But in order to get the stereochemistry right, you do have to consider stereochemistry throughout a mechanism. So you're welcome to include stereochemistry throughout your mechanism, but I won't ever check the stereochemistry throughout a mechanism. I only check for stereochemistry at the end. So if you followed along the purple lines, we did not have stereochemistry, did not have stereochemistry, did not have stereochemistry, and then poof, here's the stereochemistry on these blue things. That's kind of my expectation for you. That's enough with addition of halogens. It's time to do some mercury stuff. Crazy about mercury. We're showing this reaction next because it behaves very similar to a bromonium ion, a bromonium reaction, the halogenation reaction. Okay, so this reaction involves mercury. Mercury, this is mercury acetate. That OAC, AC is what I've drawn here. So mercury is a very large transition metal, just like bromine is a very large radius atom. Mercury gets attacked, and mercury attacks back. One of the acetates departs. Those three arrows are so similar to the three arrows from the bromonium ion reaction. We end up with a mercury with an OAC still there, and a positive charge on that mercury, just like the bromonium. But this is not a bromonium. This is a mercurinium. That's C. Mercurinium ion. Why mercurinium? Because it's a mercury that has a plus. Yeah? Mercurinium. Why did I attack the top carbon here? This carbon is tertiary. That carbon is secondary. This carbon has more substituents, therefore better carbocation character. So mercury attacks that carbon. Okay. Then I get a mercurinium. That mercurinium is not so stable. Remember, three-member rings? Three-member rings, not super stable. Not going to sit around and be our final product. So we need to bust open that ring. We've got some water around. That's a pretty good nucleophile. That's our solvent in this reaction. Water and THF are a mixture of solvents. But we've got a lot of water. Water's a pretty good nucleophile. Let's use water to bust open that reaction. And we should attack the top carbon, what we will frequently call the armpit carbon, because it helps us discuss things a little more easily. We will attack the top carbon, the armpit carbon, and bust open that mercurinium and get this. Water has attacked and brought both of his hydrogens along for the ride, and mercury is dangling off of that bottom carbon down there. Water comes to clean up the mess he made. Clean up, clean up. Everybody clean up. Okay, we get here. Well, this is not my final product. This is what has happened after step 1. This is the first reaction that we have that have two distinct steps, two distinct sets of steps. This whole thing we've drawn so far is all that happens when you add mercury acetate, water, and THF to the alkene. This series of steps is called oxymercuration, as in we put mercury on, it did some stuff. This whole thing is step 1. In the organic lab, what happens is you put all 4 of those things together, alkene, mercury acetate, water, and THF, and you let it stir, you let it heat, you let it do its thing for a long period of time. And then, after that has done its thing for a long period of time, you do step 2, and step 2 is actually the demercuration part. So this is a multi-step mechanism, but we're meaning part 2, phase 2 of this mechanism is adding NaBH4. That's sodium borohydride. It's a salt where the sodium is positively charged and the boron is negatively charged. Sodium borohydride. I need to move this mercury acetate tail out of my way so I have room to draw. So sodium borohydride, the job of the sodium borohydride is to get rid of the mercury. I've drawn it like it happens that way. The truth is the mechanism of exactly how the sodium borohydride gets rid of the mercury is not quite fully understood, but yeah, the mechanism of how you get rid of the mercury using the sodium borohydride, not fully understood, so this green step, a little bit false, but if I asked you to draw this mechanism, you would draw it like this green bit. Yeah? Okay. So the first time I recorded this, I did this whole slide with what turned out to be bad audio. So hopefully we pick up right here talking about the stereochemistry of this reaction with good audio from the first shoot. Here goes. So if we go through and talk about stereochemistry of this mercury reaction, the first thing we do is analyze how many asymmetric carbons in our product over here. Oh, none. This hydrogen is drawn out explicitly because I wanted to show you that that's where it added when we got rid of our mercury. But this is a CH2 just like that's a CH2. This branch is identical to that branch. So this is not an asymmetric carbon, and neither is that. So this green product is the one and only product that's created out of this reaction. Since we're talking about mechanisms and reactions in general, what about the stereochemistry of an oxymercuration-demercuration process? What kind of products do I get? An oxymercuration-demercuration process is not stereospecific. What does that mean? We said specific. We said that the halogenation reaction, addition of halogens, that is stereospecific. We always made an anti-product there. But the mercury reaction, oxymercuration, demercuration, does not make an anti-addition product. It does not. Goes through a excuse me. Goes through a similar intermediate as in the bromonium and mercurinium. But the overall net transformation, you do not end up with an anti-product in the mercury reaction. Yep. Oxymercuration, demercuration typically makes an alcohol product. See, said alcohol. But this made an alcohol because my solvent was water. This oxymercuration could happen in other protic solvents, other nucleophilic solvents like methanol and ethanol. Other things that have hydrogen bonding can also react here. So in those cases, we might make a different product. Maybe not an alcohol, maybe an ether right here. So this is how oxymercuration works. Beware that different solvents could be used. Maybe that's all I need to say before we click to our next stuff. Oxymercuration, you make a mercurinium. Yeah, we said that. That's a three-membered ring with a heteroatom with a plus. Bromonium, three-membered ring with a heteroatom with a plus. Mercurinium, three-membered ring with a heteroatom with a plus. We're going to see that intermediate three-membered ring with a heteroatom with a plus a few different times throughout the semester. And every time you have a three-membered ring with a heteroatom with a plus, there's a nucleophile that attacks. And the nucleophile that attacks on the more substituted side because the more substituted side has better carbocation character. It's about carbocation character because it's not a true legit carbocation. Because it's not a true legit carbocation, we do not see any rearrangements because we make mercuriniums. Mercuriniums do not rearrange. It's regiospecific. What the heck does that mean? That means it follows Markovnikov addition. What is that? It means the hydrogen gets added to the more hydrogen side. The nucleophile, the water, the methanol, the thing that attacks the mercurinium gets added to the more substituted side, the less hydrogen side. Regiospecific. Let me actually go backwards. Regiospecific. Which region gets the hydrogen? Which region gets the other stuff? So, on my alkene, the less substituted side got the hydrogen, and the more substituted side got the other nucleophile. That's called Markovnikov addition in the simplified product. What that translates to is I will never, ever, ever get this regioisomer out of this reaction. This red one over here, I will never, ever, ever do an oxymercuration and get this product. This is a secondary alcohol. This is a tertiary alcohol. I'm going to get the tertiary alcohol every time out of the oxymercuration. When this is where my alkene is, I will never get the red, I only get the green. Okay, I think I've beat that dead horse enough. So it's not stereospecific, meaning it does not give you anti only. It would give you a mixture of all a mixture of all stereoisomers if we had some asymmetric carbons. Other solvents, I've already warned you about that. Methanol, ethanol, all kinds of alcohol solvents, other things that have hydrogen bonding stuff can be used as well. Sometimes it's hard to know where to break the videos and call a topic complete, but we're going to break it right here and call this topic complete. We've talked about two similar mechanisms, both things that go through a three-membered ring with a heteroatom with a plus. They have some similarities and some differences between those two reactions, but where we're headed next is pretty significantly different from either of those, so we'll hop to a new video for the next thing. See ya!